Is it 2018 already? Postdoc, the New Orleans ACS meeting is coming up. I need data. Again. Yeah, I got a little bit of data to present, but I really need some new equipment. New equipment. Well, time to make it rain.
Damn. Yeah. Yeah. Yeah.
Woo! Nice. This is awesome. You have no excuses now.
Yeah. Yeah.
Hello, everybody. Hello. If you're hearing this, please let me know. Welcome to another episode of Ask Us Anything About Electrochemistry. I'm your host, Dr. Alex Peroff. I was out last week. My colleague, Dr. Neil Spinner, was in last week, but he is out this week. So it's just me here to try to help and answer any questions that you may have about electrochemistry. So I see Tarek says hi. Hey Tarek, good to see you. Let me give you my my boilerplate of things that I normally say during this live stream. So ask us anything about electrochemistry is an opportunity for you, somebody in just the scientific community, researcher, graduate student, to ask electrochemists at Pine Research, myself and Neil. Let's see. Oh, Tarek says the sound seems off a bit. Let me double check. Let's see. Yeah, there may be. So I apologize if there is. Okay. Some people say it is. I'll be honest. Neil's computer is actually just kind of better than mine. I've been having issues with my computer and audio interfaces. There may be some desyncing, possibly, that might happen between the audio and the visual, and that's just because of, frankly, USB-C connections. And I've been trying a couple things to try to make it better, but of course, sometimes that doesn't always happen. But please continue to provide some feedback in any of the audio visuals that happen. But anyway, welcome to another episode of Ask Us Anything About Electrochemistry. This is the first time I'm doing this for 2024. I hope you all had a good 2023. And during this live stream, we are going to try to answer as many questions as possible that you may have about electrochemistry. So whether you're doing electrodeposition, which I see that there's a question about it, IR compensation, EIS, batteries, corrosion. Some of the questions I may not be able to answer, but we're going to try to discuss them, talk about them, at least provide you with some information. One thing that's very helpful during these live streams is that your question, if you can, make them specific. Not super specific, like what's the activation energy barrier for a very specific molecule, like ruthenium hexamine or tetrabutyl ammonium hexafluorophosphate. We don't know some of those answers, or I don't know some of those answers. But at the same time, if there is a very general question, like what is electrochemistry, maybe I can give a general answer, but it might not have the depth as something like a 1 hour or 2 hour lecture that you might get from a professor. So questions actually that come in are usually about clarification of an electrochemical concept are usually the best, or how to do something is something that this type of atmosphere is always good at, or this kind of venue, I would say, is good at. We are on YouTube. We are also on Twitter, and so if you're on either of those platforms, please leave a comment in the chat, and I'll try to answer them as soon as possible. Additionally, if you are a tier 1 or tier 2 YouTube member, you can join us on Restream and actually show up on the screen and actually share data if you want to say, hey, why does my data look like this? What kind of problems am I getting? That's also another thing, a benefit to tier 1 and tier 2 members. And then the last thing I want to share with people as they come in, and I'll tell you more as time goes on, is Neil and I have started a podcast called the Electrochemistry podcast, and it launched earlier this month, January 4th, I believe. And so now it's on basically all platforms. Google right now, if you're on YouTube, Google podcasts, YouTube podcasts. It's on iTunes. It's on Spotify. It's on what's the last one? I think Audible is the other one. There's a lot of other ones like iHeartRadio, but I think those are the main ones, the main things. All right, so looking at some of the questions, I will try to answer as many as I can as we go on. Also, I apologize in advance if I mispronounce your name. I'm American, and sometimes we just mispronounce names. Also, these are names on YouTube, so you can name yourself a Pokemon for all I know, and I wouldn't even know. So let's look at some of these. Let's see. So Tamim Billah asks, I want to know basic all idea about electrodeposition. Okay, all right. Let's talk about electrodeposition. I can at least tell you a little bit fundamentally about the concept. All right, so what I'm going to do, I'm just going to switch to presentation, and let me show you my screen. I'm going to hide the question for now, just so that you can see the PowerPoint. So electrodeposition, generally speaking, is just applying a potential and depositing some kind of metal, some kind of material onto a surface. So typically people may have some type of conductive electrode surface, looks something like this. This is your electrode. It's in solution, and you may have some molecule, some little molecule, typically like maybe a metal, and it's like a metal ion, and they're diffuse in solution. And sometimes the conditions for electrodeposition will always change, but usually these are things like they're usually some kind of metal ion. So some kind of metal with a plus, so it's usually some kind of cation. And what happens is the electrode, you will apply some kind of negative bias, and you will try to reduce the metal onto the electrode surface. So maybe it's a 2+ or a 1+ oxidation state. Don't know. Depends on the metal itself and what form it's in. But then what happens is this metal will form a bond, an actual, let me actually erase that. That doesn't look very good. It'll actually form more of a bond on the surface. So if I have my metal, the electron will actually form some kind of bond. And you may have a covalent bond, you may have a metallic bond, you may have some kind of bond, but usually you form some kind of bond with the surface by reducing the metal onto the electrode surface. So that's something that you can actually do. That's the basic principle, at least, behind electrodeposition. Now, one thing that's very important, or generally speaking, people think about when it comes to electrodeposition, they may ask questions about what's the potential that you're going to apply, or maybe even a more important thing is what is the current that you're going to apply, because you can do an electrodeposition technique galvanostatically. And you may also just ask general conditions. Just what are the experimental conditions? That is bad. I am going to, I always forget that PowerPoint does have the ability to type words into the chat box. So I can actually just type in just experimental conditions. And those experimental conditions can, they can be things like temperature, stirring. Those are actually those are the main ones, but also just electrolyte composition. All of these things will end up affecting or playing a role in the deposition process. So, and also if you have questions or follow-ups, please let me know, because I can check the chat in case there's a follow-up or if there's something that is unclear. So let me also just go back. And usually, galvanostatic mode, where you have a constant current, is typically the route that most people use when doing electrodeposition. Maintaining a constant rate of deposition tends to be one of the more important factors when depositing some kind of material on your electrode surface. That's the basics, at least. And what the potentiostat does is it will vary the potential here. This will actually vary the potential that's being applied to make sure that you have a constant rate of deposition. And there's so many factors, temperature, stirring, electrolyte composition, that go into the uniformity, the speed at with which your layers are actually formed. But that's most of what I know about it. And if I were doing electrodeposition for the first time, I might do something like a cyclic voltammetry experiment with a solution of my metal kind of dissolved. You know, this, you can like buy this at the store, but it doesn't exist as just like alone. It probably has some other ligands on it that come off that need to be reduced. Maybe it's chloride or something, or this may exist as a hydrate and there's water around it, or it may exist in a non-aqueous solution, although there's not very much metal or electrode deposition on these. And the other important thing to note as I erase this about electrode deposition, I can get rid of this as well, is that typically the kind of data that people do, and there's several things, but what you might have is you might do what's known as chronopotentiometry. So your potential is varying, maybe going up and maybe going down. And let me actually just write down what the technique is. So that's chronopotentiometry. Sorry, I sometimes I say the word as it's spelled so that it's easier for me to spell it out. But chronopotentiometry is a technique that you can do to do electrodeposition. And what you'd want to do, and this is to maintain, this is to keep I, let me make that a little bit bigger. This is to make your current I, in a proper thickness, your current, to be constant. So this is a constant current. And when you have this constant current and you know the time, you can figure out the charge, which will give you an approximation for the number of moles of the species deposited on the surface. And there are some techniques such as anodic stripping voltammetry that are also used to help you determine what molecules got stuck on the surface. So that is what I would say are the basics of electrodeposition. And if you have more questions or need further elaboration about this, please let me know in the comments. Okay. All right, Tarek, good to see you again. Let's see. Hopefully I can answer this. I might not be able to. Neil is really the EIS expert. But how do you calculate the time constant for a semicircle with an RQ element using a Q or a CPE instead of a regular capacitor, given the different units of the CPE? That is a very, very good question. I would need to think a little bit more about that. Because it is in the different units, and it is in Siemens. And I think in general, because yeah, you do want, you can figure out the resistance fairly easily. I think the hope with doing this is that the units for the CPE, or at least the kind of the alpha factor for whether it's more capacitive or resistive, really leans towards 1. It really makes it a more of a capacitor than it does a resistor. I'm wondering one thing that you might be able to do is actually treat it like a capacitor, like do the circuit fitting as a capacitor, and then use an approximation for that capacitance associated with that electrochemical process. That is actually my general recommendation. I think maybe next week when Neil is in, he can perhaps give a more detailed answer to that question. But yeah, I would actually think, because it really does need to be a capacitor for you to have a time constant, because it is the charging of the capacitance. That's what the RC time constant represents. So it does need to be capacitive-like in nature. Additionally, you can always get some rough ideas, or you can always get some rough ideas about what the time constant is based on where in the Nyquist plot, like at what frequency are you observing these semicircles. So if you have more semicircles in, say, the high frequency region, that usually means it has a low capacitance. It's very fast to charge and discharge that capacitor, and hence its time constant would be lower. So that's another kind of, I would say, qualitative thing that you can do. But I'll make a note of this and see if I can talk to Neil about getting a better answer. I do not know enough about the unit conversions and how the units would change. But it's a good question, Tarek. Very good question. Let's see. All right, this question's from Mike Saraceno. I hope I spelled that right. Saraceno. During the electrochemical deposition, does the experiment need to be sealed? I don't think so. No. So similar to the previous question, just all about electrode deposition, you don't necessarily need to seal it unless you have an air-sensitive system. If oxygen or water or air or whatever plays a role, or potentially can get reduced during that process, and it affects the electrode deposition, then yes, you probably will need to at least purge or sparge or form some kind of seal. But it's important whether or not oxygen plays a very important role in that deposition. I have done some level of electrode deposition. The only experience is some of the products that Pine makes. We use a kind of a specialized solution, so it has a very specific concentration of I think it's like silver ions. I think it's called like a Cypress silver plating solution. You can buy it. You can just buy it online. And we just set it to galvanic static mode, and this is actually done in air. So it's in solution. You don't need to degas, and you're actually able to deposit silver on the electrode surface. So I know you can do electrode deposition without degassing, and you don't need to have a sealed system. So it will depend, Mike, on whether or not you think oxygen, reduction of oxygen at the potentials that you need to have happen, will affect the deposition of the metal onto your surface. So a little bit of experimentation will probably be required on that part. All right, we're getting quite a few questions coming in. I'm going to try to get to them as soon as I possibly can, with as much clarity. Okay. How to choose correct components for EIS circuit. This is from Kamal Jahad. I believe I pronounced that correctly. How to choose correct components for EIS circuit fitting. To fit the spectra I obtain, I need to adjust values for existing components and introduce additional components to, for the best fit. Okay. Yeah. So again, this is something that Neil is very good at, but I can try to give you a little bit more, a little information on just kind of what I know when it comes to EIS circuit fitting. And let me make sure that I'm going to hide your question temporarily just to give you the full screen. So let me just delete this very quickly. So I'm going to type a few things in just for clarity, but there's going to be when it comes to choosing circuit elements, one of the main things first is you need to think about it's going to be based on your electrochemical system. So you should always be you always need to think about your electrochemical system when thinking about what circuit elements to put in it. All right. So there are a couple things. Hold on just 1 second because the doors are open and people are talking out in the hallway. Okay, sorry about that. All right, so when it comes to, so there's always the electrochemical system itself, but then there's certain things in the EIS spectrum that will be indicative of like, oh, it represents this, or oh, it represents this other thing. So I'm just going to draw a couple things very quickly to show you. But so for example, let's say I just have a semicircle. Okay, I have a semicircle. Well, and this is sorry, this is Z. Sorry, this is Z real. This is Z real. This is the real impedance, and then this is Z imaginary, negative Z imaginary. Okay, just so people are aware. But you know, if you have a leading resistor, this distance is the leading resistor in your EIS circuit fit. If you have any kind of semicircle, you usually have what's known as a Voigt element. You have a resistor and you have a capacitor in parallel. That's typically whenever you have a semicircle. So if you have many semicircles, you know, if you have lots of semicircles, each one of those should represent some kind of capacitor and resistor in parallel. That is one such interpretation, sort of say. Okay. And just delete that. Additionally, if you have something like a long tail like this, you may have a Warburg element. Oh, and one thing I should note is that, and this is related to something Tarek said, but you may have a capacitor, you may have a constant phase element, a CPE. So this could also be a Q, right? So that's another thing that you may want to do. Similarly, if you also find yourself with these loops, so sometimes people see little loops in their EIS, or they may it'll look a little bit more have the same kind of plot. Sometimes you'll see these kind of inductive loops that kind of cross over and stuff like that. That means you have an inductor somewhere in your system. Additionally, if you have EIS, if you have some Nyquist data, some Nyquist plot data, where the high frequency region here has a positive Z imaginary, that is usually indicative of a leading resistor. So you would have something like a resistor and then a some kind of leading a leading inductor, leading resistor, leading inductor, and then you actually have your the rest of your electrochemical system. This is usually attributed to cable inductance. So you usually just need to delete it or get rid of it or account for it in some way. But this is not associated. This is typically not associated with a electrochemical process that you're interested in. Inductive loops have always been kind of triggering for me, and I don't fully understand them and how they happen. But my limited understanding is that if you have a chemical system, an electrochemical system where you have, where you say have, I'm just going to call it an interface, and let's say you have, like, let's say you have iron in the 2+ oxidation state, and you have iron in like the 3+ oxidation state. Inductive loops occur because there's electron transfer between these two interfaces in the mid to low frequency region. And this is indicative of a kind of electron transfer process between these two things, but there's no inductance. Or sorry, there's no inductance. There's no capacitance. Like, there's no, this interface is not defined by a Voigt element like a resistor and the capacitor in parallel. Actually, there should be no space there. Should be no space there. Sorry. So that is something just to keep in mind. But that's there's a lot that goes into choosing them. There's also these things called Warburg shorts, where instead of getting this tail that goes like this, you end up getting something along these lines where it goes up, it goes out and up. It's like there are certain blocking conditions, diffusion length limitations. So these are some of the things that you need to think about. You need to think about your electrochemical system, but you need to understand and think about, like, okay, every time I see a semicircle, I usually have some kind of Voigt element, a capacitor and a resistor in parallel. There may be other aspects of your electrochemical system that might mean there's actually an embedded system. So you may have something like a capacitor and a resistor, but you also have a resistor here too. So you may have these kind of embedded systems where resistors and capacitors are kind of all in the same parallel circuit. It's a lot to go over what circuit elements should you use and stuff like that, but you really must think about your electrochemical system. Think about what does it physically mean, and then use a circuit element as a very simple model of that process that's occurring. So hopefully that makes some sense, or at least gets you on the way for deciding what circuit elements to choose in your electrochemical system. Hopefully that was helpful. I see we're getting more questions. I will try to answer them as they come in. And let me just check Twitter very quickly. It doesn't look like anyone is asking us anything on Twitter, so that's great. All right. Olusola. When I run my CV, I tend to get increases in the area under the curve. What does that mean? Now, it's a great question. So, when you do signal voltammetry, it could mean several things. But let me again go to this presentation and see. I'm gonna hide this for now. So you get increases in the area under the curve. So it could be several things, but let me at least just kind of draw this out a little bit. So you have voltage, and then you have current, and then you take one cyclic voltammogram, you get something like this. All right, it's your duct. And then you take another cyclic voltammogram, but maybe you get something like this. This is like this, or something like that. And then you do another one, you get something like this. Do something like this. Every single time as you sweep and scan, you get these increases progressively going up, maybe going out the other direction as well. So leave a comment if that's something that you're observing. So what this can be, what I've usually attributed some of this to, is there's usually some additional. So this kind of response, and maybe it's not exactly like this. it's usually associated to some change in the surface of your electrode that you're doing some reactions on. It can be attributed to the formation of an adsorption layer on top of the surface. So what that's to say is if you have an electrode, this is at least a possibility. Not to say I know for sure. But if you're reducing something onto the surface, let's say you have the following. So I'm just going to write, you have an oxidized thing plus an electron, and it gives you a reduced thing. Okay, so that's the redox reaction that we're looking at. And go back to my tool. So what's happening is OX, I don't want to say diffuses towards the electrode surface. You just have some OX here, and then you have an electron, and then it forms red, the reduced form. So normally that will reduce and diffuse away slowly. Over time, it'll move off the electrode surface. However, there are instances where this will irreversibly stick to the surface. That can happen. You can have this reduced form stick to the surface. I don't know how it gets stuck, but it gets stuck. And it doesn't actually diffuse away. This process right here doesn't happen. And there are techniques. There's chronoamperometry is a great technique to determine whether or not you have an irreversibly formed species on the surface. But what happens is when you apply the potential again and it goes down, right? It's going down. You're right here. You are oxidizing. This is going back to the oxidized form. However, it's oxidized, still stuck on the surface. It's still stuck on the surface. So the next time you do a sweep, you're here, you're at this point, you got to reduce this guy with an electron, but you also got to reduce another another OX, another oxidized form of this with another electron, so you get more current. And sometimes there may be some sites that are not fully taken care of in the first step, but this usually happens where continuous cycling back and forth slowly grows this kind of layer of stuff on the electrode surface. But I am pretty sure if you cycle the potential enough times, if you keep sweeping the potential enough times, you will reach a steady state. There will be a point where your surface will just have lots and lots and plenty of maybe a surface monolayer, say, of these molecules on the surface. So that is one thing, and this also changes the the double layer structure a little bit. So there may be some changes in capacitance, but that is my hypothesis for why the current or the area under the curve keeps getting bigger as you cycle the potential more and more during the experiment. So hopefully that is helpful. Just going through the questions. Let me know if you need further clarification. Oh, wait. All right, here we go. So he says, yes, I'm observing. That's what I'm observing in my battery system. Okay, so that so I don't know as much about batteries as Neil does. Mostly, are you doing this in a? So I guess the question that I propose to you is, are you doing cyclic voltammetry in a battery? Because from what Neil has told me, you rarely would do cyclic voltammetry in a battery. It can actually be it can be dangerous to do cyclic voltammetry in a battery, just because the voltage is. Oh, all right. It sounds like I answered this question, so I don't need to elaborate on that much more. Okay, good. Of course. If you have any other questions, I'll be happy. If I didn't fully answer it, please let me know. All right. Ifra Bashir. Let's see. I think, all right, he has two parts. To study the overall cell activity by utilizing our prepared anode and cathode, mostly two-electrode system is employed by taking the counter as a reference electrode. Why is this so? There's a little bit of a continuation, which is say, however, it is well known that a three-electrode system should be used unless the ultra-microelectrode working electrode or a small current is used. Yes, some people can do that. You don't need to, if you have a very small area working electrode, some people do not use a potentiostat. And that's because the potential actually remains relatively constant in these. When you have very small currents, nothing happens. But I think I can try to elaborate a little bit more of this question. Mostly two-electrode is employed by taking the counter as a reference. Why is this so? So let's just talk a little bit. Oh wait, hold on. Ifra has some more comments I will go over. Let's see. So let's see. Otherwise, the counter electrode potential cannot be maintained constantly. I have received a following comment on LSV for the overall cell activity. That is, it is very strange that the authors carry out the LSV experiment with two-electrode system without introducing a reference electrode. It is well known that three electrode systems should be used unless UME working electrode or very small current is used. Otherwise, the counter electrode cannot be maintained. How should I answer the comment? Okay, all right. I think I understand. Thank you for all these comments. I think I understand a little bit more about your situation. However, my answer may not necessarily help you in addressing the reviewers' comments. But this is the science. This is the general science behind this comment. All right, so let me go to this. Okay, all right, so let me delete all this. And Ifra, if you have any comments, or anybody else has any comments about this or clarity, please let me know as I go through this. Let's see, how do we do this? So let's start with a two-electrode system. I'm just gonna have a big cell here, okay, and I think everybody can see, and I think also, yeah, so I have a big cell here, and I'm going to have my working electrode on this side. Just going to make this, so this is working, and then I'm going to have counter. Okay, so then I'm counter. Counter is also going to be big. This is all you need to know right now. Okay. So when you have when you apply some kind of potential, a power supply, for example, between these two guys, you're going to get current to flow. I don't know what direction it flows in. We're going to get current to flow between the counter and the working electrode. That is commonly what happens. Now, how does current flow? Current flows through migration, the movement of ions, but it also moves through reactions. That's how we think about it. So we talk about an oxidation. Let's say we have an oxidation reaction, for example, on your working electrode. Oxidations are occurring, which actually technically means the current's going the other way, but it doesn't matter. If oxidations are occurring on your working electrode, a reduction reaction must happen on your counter electrode. You have to have charge balance. Something has to be happening. So your counter electrode always has these, if there's one happening here, there's one happening there. There always must be charge balance. Now, when you do this, when the voltage is applied between these and current flows, the interfacial potential of the working electrode changes. it changes to the voltage. It usually changes to the voltage. The voltage represents a difference. Remember, if I have a +1 volt, for example, between the counter and working electrode, you can almost think of it as the difference between the potential of the working and the potential of the counter, which is to say that maybe the working electrode potential is something like 501, and this is 500 volts, and but the difference between them is 1. It's only 1 volt. But man, this is 500. It's pretty crazy, right? But this is just 501. So there's a relative scale that kind of has to happen in these things. We don't know what the potential of the counter electrode really is. We only know the difference. That's what's happening when you use, say, a power supply or something, or in the case where you don't have a reference electrode. Let me just make sure there's no follow-ups. Okay. So you have double layer charging, you have oxidation reactions occurring in the working electrode, and all the opposite stuff has to happen on the counter electrode, which means that the potential of the counter electrode is different. The potential of the counter electrode is changing, right? That has to happen. The referee's comment about only with ultra micro electrodes being okay has to do with the fact that there's not that much of a change. When you have milliamps or microamps of current flowing at the working electrode surface, the potential of the counter electrode and what happens at the counter electrode has to be significant enough to counteract that change, right? If I have a million reactions happening at the working electrode, I have a million reactions happening at the counter electrode too. But if I only have, say, a nano electrode and I have nano or picoamp currents flowing, there's so little that's happening at the counter electrode, so little that the potential of the counter electrode is relatively constant. You can have, if you know this value very well, that's fine. That's not a big deal. So that is to say that the only way you can respond to your author truthfully is if the current is very small, nanoamps, picoamps, you can effectively say that the counter electrode potential really hasn't changed, and the voltage difference between either a counter reference hybrid in a 2-electrode system is sufficient enough for an analytical technique. Now, most people use 2-electrode setups mostly sometimes for like bulk electrolysis. Like, I just need to do bulk electrolysis. I really don't care about the precise voltage. I'm literally just trying to convert one thing to another thing. And so the exact potential doesn't even matter. It actually varies. They'll do a chronopotentiometry experiment. They just have a constant current. The voltage is allowed to fluctuate to get that reaction to go at a constant speed. But if you're doing an analytical chemistry technique where you're trying to get like a specific voltage and say, oh, the redox potential of my whatever species or whatever system is X, and it's just via a counter electrode, it's probably not going to be very accurate. A lot of this has to do with the IR drop. So there's solution resistance between the counter and working electrode. In a potentiostat setup with a 3-electrode cell, the IR drop is really between the reference and the working electrode. But that's really about it. There is solution resistance between these two things that does affect kind of the interfacial potential of the working electrode and the counter electrode. So this is a lot, but hopefully this is helpful. It really depends a bit on the only thing I would say you can do, and maybe is you may need to get a reference electrode. You may need to do an experiment to just make sure, just to confirm that your reference, that like the potential you've cited is actually correct. So that's kind of my 2 cents on this situation when you're doing like LSV and stuff like that. So, Ifra, if you want to tell me a little bit more about your electrochemical system, maybe I can provide you with some more assistance. But based on what you described, I hope that's a little helpful. I can talk a lot more about reference electrodes if you want to know more about them, because they are my favorite and not favorite subject. Abu, let's see, I don't think I've, wait, hold on. There's another question prior I want to get to. Tamin has just a follow-up, and then I'll get to Abu afterwards. Hopefully I can answer this relatively quickly. In electrodeposition process, why we see reduction first, then oxidation? If we see oxidation first, have any problem? Reduction first, then oxidation. I don't know exactly. I would need to really see the data to see what you mean by reduction then oxidation. If you are doing a cyclic voltammetry experiment, instead of holding the potential, you sweep the potential. There's a chance that you sweep the potential back, so you reduced something, and then you oxidize it on the way back. The oxidation has to be done. That has to occur if there's something that was reduced earlier, or if the molecule is in a state where thermodynamically you can oxidize the species. So if you reduce something and you haven't kept it or held it at the potential where it's stable and thermodynamically reduced, then it'll oxidize when you disconnect the potentiostat or if you don't have a stable system. So I might need to know a little bit more about exactly what you're interested in or what it looks like. So you can tell me more later. Let's see. Okay, Abu, let me get back to your question. How to know if my sample is relaxed between doing EIS analysis? That's a good question. Neil definitely knows a little bit more about it, but I think a lot of it actually has to do with, let's see, know that it's relaxed. So usually it's the OCP. I always think about it from like the OCP standpoint. So if you have applied a potential and you oscillate your system, you've kind of perturbed it, but you haven't perturbed it enough that it's like it should be super crazy. You'd want to take OCP, and if you really want to have a detailed look at this, you take OCP before and after doing, say, an EIS frequency experiment. So if you do, say, let's just say you do OCP, you have a value for the OCP, you've held it, you've measured the OCP over, say, like a minute or 2 minutes or however long until it's stable. You do EIS, let's just say it's at like 1 kilohertz. And then you do OCP again, and then you see, all right, did my OCP change by doing it? That's a very specific analytical way of doing it. But really, the other thing, and I'm going to channel my inner Neil to try to figure it out, is your EIS data will not be valid if your sample is not kind of relaxed in between each step. So you'll definitely get some Nyquist plots that look odd. They'll have some noise in them, and they'll look like outliers. And if you do Kramers-Kronig analysis, you'll find that the Kramers-Kronig analysis does not give you good results. And I mean, you'll see, and if I just kind of show you on in a very general sense. Let me delete all this stuff. Delete you too. If I do this, So if I have my Nyquist plot, right, so maybe it's here, but then, or if my Nyquist plot's actually like dots, right, so if my Nyquist plot's more like these big dots, nope, I want a thick dot, thick dot, thick dot, because you'll get at each of these frequencies. And you have something like here, you know, I'm just kind of making stuff up, but you know, you'll have this noise if like you get these parts that don't, you know, that aren't working. You know, you're getting these weird values in the Nyquist plot. Of course, this is like negative z, imaginary, and then you have z real. Just notice something. This looks a little bit like a face, just a little bit. But yeah, you'll get noise. So that is my thought about determining whether the sample is relaxed in between. And I believe in our aftermath software. Let me just double check. But one thing you can do to kind of solve this problem is if I go to impedance, and we're always kind of changing these things around a bit, you'll be able to adjust. There's actually, I think, an advanced setting. I know there's a version of our software. We're constantly updating the software, but yeah, here we go. Interfrequency settling period. So if you look here, you should be able to adjust, say, the interfrequency settling period. And this allows you to say, oh, you know, if you're using a reference electrode, use a reference, or if you've measured OCP, use OCP. But you can actually change how long you want to hold the potential at a specific point. Just hold it, make sure that it's stable before doing the next EIS frequency. So your experiment might take longer, but this would be the way you could change it. So hopefully that is helpful. All right. I'm going to. All right. There's a lot of. A good number of interesting questions coming in. Let me see. All right. So let me see. Let's see. All right, Wyatt. Wyatt. Hello. When I test for dopamine using DPV, I get one oxidation peak, but when the scan is about to end, it has another oxidation peak, but it's not a big peak like the first. And I'm guessing why you're interested in why you're getting this. I'm not so sure. I haven't used dopamine, or I haven't done electrochemistry of dopamine before. I know that's used a lot in, say, the fast scan cyclic voltammetry community. I believe dopamine, yeah, it gets oxidized, so there is a possibility that you are generating something. But let's see. When you first scan, before it's about to end, you get a second. It could be contamination, very simply. It's always possible. I'm just going to guess a little bit what your DPV might look like. It's not going to look like a happy smiley face, but you know, DPV it's very similar to cyclic voltammetry in the sense it's a current versus voltage, but it's much more kind of clear. But usually get very well characterized peaks. Very, very well characterized. But I'm assuming you maybe have like some little thing over here. That's my guess. I'm thinking it's somewhere off, or maybe it's here. I can't imagine it being in this region. But yeah, I would think that it might be some junk. Do you see, the question I have is, do you see it in cyclic voltammetry? There may be some contamination. This very easily can happen. But if it's showing up in DPV, it's probably something very real in the sense that it might be a real contaminant. So I'd have to know a little bit more about it. And I might assume you're also doing this on carbon. There shouldn't be much on carbon when doing dopamine oxidation. I'm not 100% sure. But I'm guessing it's probably a contaminant, and it can even be a contaminant of. I've observed weird things with, say, like if there's lead, like I've seen like weird lead oxidation peaks because like there was a leak in the electrode, and there was, they might use a lead solder or a tin solder, and that shows up. So that might be another thing, possibility. I have to see it. Let's see. Oh, slow. Why is it dangerous to do CV in a battery? So the limited, my very limited knowledge of this is that you might be able to do CV in a battery. I don't know for sure, but the idea is the battery has a very specific voltage. It has a specific charge and capacity, and sweeping the potential can current becomes the dangerous thing. So you're kind of constantly increasing that voltage, or that voltage difference, and you're just going to get more and more current. The battery might, maybe I think in some cases, explode. Just how much current shows up. I would have to ask Neil a little bit. It might. I mean, I think people do perform CV on a battery in a safe setting. Maybe it's at very slow scan rates. But my understanding is that most people just do charge discharge when they are studying batteries, maybe doing some EIS. But the idea is to really not perturb the battery that much by adjusting its potential, especially if you adjust the potential beyond its limitations. But yeah, I don't know. I think it's a current thing, and how changing the scan rate affects things. This is again a Neil question. Hopefully you'll be able to pop in next week and then ask it again. And then Neil might say, Alex, you're wrong. You can actually do CV on a battery, no problem. I'm like, oh, didn't know that. Let's see. Honest Makamba, I think it's Makamba. What is the best approach to create polarization curves? Why are these polarization curves so important? Well, it depends what you mean by polarization curve. A polarization curve, very generally speaking, and let's go back to just sharing our favorite here. Actually, this is a polarization curve right here. So if I just delete this, polarization curve is just a current versus voltage curve. And one of the best ways to get one is by doing cyclovoltammetry, just scanning the voltage and measuring the current response. So sometimes you get, this is a typical duck cyclovoltammogram. But if you're doing something like, some people get polarization curves for, say, solar cells, and when you do things like polarization curves for a solar cell, you'll know a little bit more about, like, okay, with the light turned on, at what voltage do I see a huge current spike, or when I don't see a huge current spike? And that gives you a little bit more information about, say, like the band gap of your solar cell. So polarization curves just in general are like, you're looking at the current versus the voltage. That's what a polarization curve fundamentally is. Some people scan very quickly, some people scan very slowly. Some people look at, actually they flip it, they look at the voltage as the current changes. But that's what a polarization curve is, just fundamentally. And it depends on what you're doing as to why it's important. But hopefully that reason about solar cells is helpful. But also, cyclovoltammetry tells you more information about the redox properties of molecules. So a lot of people study for that, for catalysis, batteries, things like that. Okay. All right. There's a bunch of questions coming in. I'm just kind of looking ahead a little bit. Okay. Mahesh Falak, I think. Which is the best method to calculate Tafel plot using LSV curve, chronoamperometry, or EIS? How to do that? So my colleague Neil recently did actually did a webinar earlier in December about using an RDE to calculate a Tafel plot. So an RDE is a rotating disc electrode. I'm not sure exactly what the absolute best method is to calculate a Tafel plot. Most Tafel plots are all done, they're done using cyclic voltammetry, like LSV. Of all the techniques that you listed, I think LSV would be the best, but you would need to go at very, very slow scan rates to get that, because you're trying to minimize your current data or you're trying to minimize the impact of double layer charging on your current data, and you're hoping that the current response you get is truly the kinetic current that is associated with the electron transfer. And that's one reason why, of those three techniques, we, in Pine Research, myself, Neil, we recommend using a rotating disc electrode as the method to do that. And for a very complete description, I'd recommend watching Neil's webinar. It's for Tier 2 YouTube members. Each webinar is about an hour long, and it goes into way more detail about setting up a rotating disc electrode with ruthenium hexamine and the actual calculations for making a Tafel plot. So that is something that's hard to do right now in such a short kind of time span, so to say. But I would recommend doing that. I will, I'm going to let me go to the Pine Research YouTube channel, and then I'm going to find his most recent webinar content. It's for YouTube members, but if you but you can join, and it's like $10 a month. But if you just get it, watch it, you can watch all the extra content and stuff that we have, and that will allow you to see everything. And then just cancel your membership afterwards. Let me find the most recent webinar thing. Give me 1 second to find. All right. Experiments. It has a few of these. I'm going to copy this link. All right. So I'm going to, in Restream, just put it here. So hopefully you will see it. And when you click on it, you'll notice it's going to ask for membership, but you'll be able to watch it in completion. And there's also a part 2. So there's a part 1, which goes over rotating disk theory and doing experiment. And then the second one is data analysis. And that's actually the calculation of a Tafel plot and getting the Tafel slope and the current exchange density and things like that. Okay. To calculate transference number, you need interfacial resistance at initial and steady state. How to find those values? Are we using EIS spectroscopy to the symmetric cell after taking DC polarization? So let's see. Ooh. To calculate the transference number. So if you're using EIS, okay. All right. So I can help you find. So the transference number and or interfacial resistance is the. It sounds to me like the charge transfer resistance. That's what you're talking about. I can help you. This is my somewhat limited understanding of how to solve for it, because I haven't actually looked up the transference number before. I've heard it a few times, but if you do EIS and you get something like this, maybe that something. So you're going to get some Nyquist plots, and this Nyquist plot might be at a specific potential. You apply a sine wave across some E naught, negative Z imaginary, and then Z real, and then let's say this is a simple electrochemical system. You have a solution resistance, and then you have double layer capacitance, and then you have your charge transfer resistance here. So I'm just going to type these in so that it's very clear. But this is your RCT, and then this is your just we usually call it RU, and then this one is your CDL, and that's the double layer resistance, or sorry, the electrical double layer. So you are trying to find this. So what you're going to, and this value will be different depending on the potential, because the charge transfer resistance for a redox molecule is a function of the potential. Like if the potential is at a point where it's very easy to do electron transfer, then you'll be able to find. So let's say this is a CV. It's not a very good one. Voltage, current. Perhaps the initial state that you're talking about is here. If you do EIS here, you'll get some very high number for RCT. But if you decide to do EIS here at this electrode potential, and you know this guy is this guy, you're going to get a very low RCT. And that's going to give you, that will give you at least a difference in the charge transfer resistance. Now from that point, I actually don't know very much about how to, oh, and I just realized that I should hide this so that you can see. At this point, I actually don't really know that much about the rest of your question, but hopefully that's enough to help you, you now know what the interfacial resistance is. And I think what you mean by initial and steady state value, EIS needs to be done at a steady state. That kind of needs to happen from my understanding of it. For valid EIS, it's got to be linear, it's got to be stable, it's got to be causal. Those are all the things important in getting EIS. So I wish I knew a little bit more about transference number, but hopefully that helps you. Okay. All right, just looking through. Ifra says, thank you. His system is in current milliamp. Oh, and he says system is in milliamps per square centimeter. So, yep, that's a lot of current. That's probably it's probably not gonna make your case about 2 versus 3 electrodes. Very good. Let's see. Mike asks, thank you for the live chat. You think you post links to educational videos on basic deposition? I don't know any. Maybe in the future we'll develop some, but personally, I don't know any. I'd probably have to do some searching, but a lot of the stuff is on Google. It's on YouTube. Sometimes it's hard to find exactly what you're looking for. But papers would also help or be good. One thing I can at least put in the chat that might be helpful. Give me a second to find it. There was a lab that Pine Research developed that might be helpful for you. And this was exploring, I'm going to put it in the chat right now. It's exploring Faraday's law. And this is a lab that basically has to do with electrode deposition. You use these inexpensive screen printed electrodes. It has a couple solutions that you need to buy, but basically the lab itself is actually about electrode depositing something and then backing out Faraday's constant by like the charge that's passed and the mass change of the screen printed electrode to the moles of the molecule. So it's a cool lab, but it's a great introduction to electrode deposition and basic deposition. But no videos, unfortunately, no videos. Maybe in the future we'll make a video on it. But I've got so many other things going on. Let's see, Muhammad Nauman says, which material method is best to synthesize the working electrode? And I think he has a little bit further explanation. If I understand instrumentation, and please tell us for nanomaterial electrodes, which material method do you prefer? You preferred for perovskites. So I'm not so sure. When people are regarding synthesis, I don't know how to make, and I don't know how to synthesize anything. I have to like look it up. And are you talking about organic synthesis? It looks like you're doing inorganic synthesis to make a nanomaterial electrode. The only way I am aware of making any kind of nano electrode is to use something like a glass capillary and a laser puller. And that's a system where you have a glass tube with the metal of interest or the material of interest electrically conducted and connected to a wire. A laser shoots at it, heating it up, and it slowly pulls the glass apart. And what it does is it creates a very, very, very tiny, narrow, on the micron to nanometer scale working electrode of the material. But to make a perovskite nanomaterial working electrode, I'm not 100% sure. One possible thing that you can do is if you could just create, say, not a nano, but like a macro or a micro electrode, even if it's a millimeter, millimeters or so in outer diameter of your perovskite material, you can do things to cover parts of it. I use a material called Torsil epoxy to actually cover it's a fairly inert epoxy material to cover portions of my electrode. And while there's no way to really control it on the nanoscale, there may be a way you can actually get a very, very small gap in the nanomaterial. But truly, I don't know. I'm just throwing an idea out. Torsil epoxy to help you mask, or if you can create a nanomask, actually that's the way to go. If you can create, say, a nano mask where, you have a thing and it's just 1 nanometer hole, and you can put it over your material and it's insulating and it only exposes a nanometer of your perovskite material, that might be another method. And I would, if I were you, I'd talk to people in perhaps like the AFM or STM community, any kind of probe microscopy group might be able to help. Just a thought. So let me go and just double check. Okay. Okay, can you speak about negative and positive potentials in electrochem? I guess I can. Not so sure what exactly I would say. Because it's a very positive and negative potentials are very well, first off, the main thing is that they're relative. In electrochemistry, your reference electrode creates a stable reference point in your electrochemical cell, and you can tell a potentiostat to apply positive or negative potentials with respect to that reference electrode point. So, and one thing that commonly gets confused or is confused by people is that the charge on the electrode is not always, if it's a negative potential, do you always have negative charge? And if it's a positive potential, do you always have positive charge on the electrode surface? And the answer is it's complicated and usually no. Sometimes it's different. There are cases where applying a strong negative potential does not give you negative charge on the surface. And almost quite literally, if you have a negative potential, you're attracting positive cations to the electrode surface, so the surface charge may actually be more positive at the electrical double layer. But the potential is usually done in such a way that, relatively speaking, if you're trying to induce an oxidation or a reduction reaction, you're moving the potential of that working electrode, positive or negative, of the redox potential of a species, and you can induce an oxidation or reduction reaction. It's kind of my general, just a few words on negative and positive potentials in electrochemistry, but that's perhaps all I would say. Yep. Also, yes, please pop in next week when Neil is in. He will give you a lot more about batteries, way more than I do, and he also knows way more about the safety of batteries too, because he worked on that stuff. Okay. Abu says, Bard seems a little complicated. Is there any other book you could suggest to understand electrochemistry? I would agree. I do think as much as Alan Bard's book is extremely comprehensive, I also do think it's a little bit complicated. The only other book that I think is a little bit easy to understand is let me find it. Electrochemical. No, not electroanalytical. Yeah. Let's see. Here we go. So I'm gonna put the Amazon link in the description for you, and I'll just share my screen so that you can see it. So it's a yellow book called Laboratory Techniques in Electroanalytical Chemistry. I find it to be very useful when it comes to actually doing lab techniques. That's the main thing. Like, just doing the lab techniques is good. But I also think it's one of the more instructive when it comes to understanding some of the fundamental concepts. But that being said, I agree. There are not that many good or even great books at conceptually understanding electrochemistry. And I believe part of that is because we're in like a very small world, sort of say, like DC voltammetry or AC voltammetry, corrosion, all those types of things are actually relatively small when it comes to electrochemistry and understanding it, and people don't. We don't really. It's not described very well conceptually. I would just say that. All right, Fiasistos. Hello, for battery research, what is the difference between EIS and nonlinear EIS? Do we get more information with nonlinear EIS? So, I do not know what nonlinear EIS is. Neil maybe knows a little bit more about that. I know EIS needs to be linear in a way, and so I guess my guess, though, is that if I had to take a guess, and this is just hypothesizing, it just means that the applied potential wave that the sine wave that you apply, or the cosine wave that you apply, is it's kind of non-linear. It's like it's a more complex sine wave that actually gets applied. And so maybe in principle you can get more information with nonlinear EIS, but it may also be more complicated and more finicky because you are dealing with complicated wave mechanics that, EIS is already very complicated. So I'm sorry I can't answer your question or provide more clarification, but I really don't know very much at all about nonlinear EIS. Hamas, which method is best for the synthesis of process perovskite? I'm not really so sure, because perovskite is a kind of it's a type of material. It isn't a material. Like, there are many different types of perovskites, and I don't know which one's the best one for water splitting. So I'm sorry, Muhammad. It says thank you. Good. I'm glad that you liked the videos on impedance. I'm glad that they were very helpful. Stay tuned for more stuff. Hopefully, when Neil gets back next week we kind of help each other on these on these live streams when it comes to what answers, what questions, and then giving each other like a break for answering the question itself. But it looks like I've gotten through all the questions. We can wait a little bit longer to see if there's any new questions that come in. And I'm sorry again if I was unable to answer your question. There's sometimes like I don't know specifically which method or which technique is the best for creating one specific thing. A lot of these sometimes these require like a deeper dive into the literature. But yeah, definitely asking us a question about it is good and helpful for just getting us to think about it, like where it is. But sometimes the literature is the best place to look when it comes to like getting a very specific answer like that. But a fundamental question about like why your 2 versus 3 electrode system and why having a reference electrode is very important for your experiments. Yeah, we can talk a little bit more about why that's key, why that's important. Let's see. Muhammad asks, is the circuit diagram in EIS made by software? Yes. So, for example, I'll just show you on our Aftermath software. I think you can see. I will just make sure I remove. So I'm just going to remove this here. I'm gonna make this big because it's a little bit hard to see. But this is like our Aftermath software, and there are things like circuit fitting and simulation. So I'm just going to do a circuit simulation. But as you can see, we provide, and most companies do this too. Oh, I see. There is actually, I need to share. That's a pop-up. Let me share. I'm going to try to share this other screen because we have a pop-up in the, here we go. So let me just check. I think that you guys can see this. Give me 1 second. I'm just going to confirm. Yes, okay, so you should be able to see this. But this is just the different types of circuit elements and circuits that you can do. But you can build a circuit as well. And again, I want to make sure that you can see the circuit built. Nope, I gotta stop sharing and share again. I will show you that you can build a circuit. So here we go. So you can build a circuit. So your circuit design is here. So I'm just going to make something very quick. You drag and drop, resistors and capacitors or constant phase elements or inductors, and then you just kind of link them together as you need and stuff like that. And this is a way you can build the circuit. So it's in the software. Doing this by hand is, I'm not going to say it's impossible, but it's very hard. I don't want to have an inductor in my system, so I'm going to get rid of this inductor. I'm going to delete that component. And then you make sure it's in the out, and then as long as it's valid, you'll be able to make a custom circuit. So yeah, you can do that. You can make all those things happen. So yeah, so that's it. Oh yeah, sorry, Pritesh. I think you asked a question. Sorry, I missed it. There's a lot of questions. At least I think you sent a question earlier, but about electrochromic devices. Here we go. Sorry. Sir, how the electrochromic property can be measured? What are the external component need to be attached? Yes, so electrochromic devices are things where the electrical potential actually affects the color. One of the most popular, well-known electrochromic devices, they have, I think on some airplanes, the windows, you can actually push a button and it goes from like, see-through to like dark or fade, so you don't get blinded by the sun. So what you need to do to measure properties in an electrochromic device, from my understanding, is you need a spectroelectrochemistry set. You need something where you can apply a potential to your electrochemical system, and then measure the spectrum, the absorption or transmission of light. And there was a video that I made a while ago. I just want to point to one part of it. So let me just grab that video quickly, and then I'll just show you so that you know or are aware of. Let's see. All right, so I'm gonna let's go here. Let me view it. Give me 1 second to actually. All right, so that's good. Okay, so I'm gonna hide your question for 1 second, and then I'm just gonna show you here. This is a video that we did. So this is a honeycomb electrum from Pine. Let me just make sure that this is visible. And I'm gonna make this full screen so that you can see it clearly.
Aftermath, as well as physically what's happening in the honeycomb electrode. So as we start to reduce methyl viologen from the dication, which is colorless, to the radical cation, which is blue, we physically see a blue purplish color form in the honeycomb electrode, and we start to see in the UV-vis absorption this absorbance in the UV and the red, which is giving it its blue color. Okay, so after our spectrum.
This is me a long time ago when I made this video. So that would be what you need to actually study electrochromic devices. You need some kind of spectrometer, typically a light source, some kind of spectro-electrochemical thing, maybe like a honeycomb electrode, or ITO is another. ITO electrodes are like kind of a conductive glass that you can do redox reactions on, but it's transparent, so you can shine light through it. A lot of conductive materials are not transparent. So yeah, that's what you need: potentiostat, spectrometer, light source, fiber optic cables, those types of things. All right, we'll wait just a little bit longer to see if there's any other questions. But I think this was a good run, generally speaking. Neil and I usually do this for about 2 hours, and it's an hour and a half, so I think that was good engagement. And I'm glad that people come. And if you watch this after the live stream, there are timestamps in the description below that you'll be able to see once we get to it in a few days. You'll see all the timestamps, so you can see all the questions that were asked, and if there's a question that's particularly interesting to you, you can go and follow it. Some people also like to, I think, just keep this on in the background, almost like a podcast, which is something new that we have. We have released a podcast that you can get on Spotify and Apple and YouTube, Google, a lot of different podcast platforms is where you can actually listen to the Electrochemistry podcast. But you can also listen to this live stream as well. This is also helpful. Muhammad asks, is Aftermath available on the website? Yes, Aftermath is available on the Pine Research website. And I will put a link in the description below. Sorry, I'm going to just put a link in the chat. A link in the chat where you can download Aftermath. And there's a bunch of tutorials on our website on how to use Aftermath. You'll be able to import and export data if you're not using one of our potentiostats. Of course, we always encourage you to hopefully use a Pine potentiostat in the future if you are in the market for one. But Aftermath works on PC computer, and it's a great data analysis tool, both for EIS circuit fitting, calculations, things of that nature. So you can definitely do EIS circuit fitting with Aftermath. Okay, all right. Let's wait a little bit longer. Yep, next week Neil should be back in. Let me see. Oh, you have another thing. Let's see. Ertan asks, when viscosity of solution increases, how do components of impedance change? I'm not so sure. I would imagine that the resistance changes, the solution resistance. If it's harder for ions to move in solution, I would just suggest that the what's referred to as the uncompensated solution resistance is going to be the main thing that's going to affect the impedance data. That is my first guess when it comes to changes in viscosity. But it really has to do with how easy is it for ions to move and get around. That's going to be the main thing. The current will change with viscosity. So this is shown in rotating disc electrodes. The kinematic viscosity does play a role in the diffusion of molecules. You'll actually get the viscosity to the 1/6 power affects the limiting current in an RDE experiment. But it's kind of interesting because I would imagine that if the viscosity increases, it's harder to get current to flow, but that might not be the case because if the viscosity increases, the current still increases, unless it's no negative though. Levitch equation. The Levitch equation. Oh no. The Levitch equation states the kinematic viscosity is to the minus 1/6 power. So as the kinematic viscosity increases, it means that the you have a fraction in the denominator, so the current would decrease. So it would increase the resistance. That's that could be that could happen. That's my general thought right now, which I think makes sense conceptually. I think this is pretty good. I like to stick around for a little bit, just to make sure there are no incoming questions. But if you have questions, I'm going to check Twitter, just to see. It looks like there's not much happening, which is fine. It's fine. Please let me know. Hopefully there's no major audio issues or sound issues. I'm also gonna. Yeah, okay. Sounds. I have this playing in the background. Yeah, any questions? I'll stick around for a little bit longer. But if not, then I will probably head out soon-ish. Couple things. I think if there's any. I wonder if there's any announcements. Really, the podcast is the main thing. We're hoping. I think Neil's hoping to do some webinars. Pine Research is going to be out in the open, in the wild, doing trade shows, visiting labs, things like that. Of course, if you have questions or want to visit, please contact us, and we will continue to hopefully have more and more of these live streams in the future every Friday that start at 1 p.m. Eastern Standard Time. And of course, if you can't make it because of time zones and things like that, if there is a question that you want us to answer, write it in the chat or send us a message, and then the next time we will try to answer that question. It even gives us a little extra time to think a little bit more deeply about what the question is, and then give you a more thorough answer. So we usually try to do that to answer questions that we get in YouTube comments or from webinars or email, even on the telephone, those types of things. So please feel free to do that in the future. Okay, everybody. I think that's good. Thank you for tuning in, and I think this is very productive. Please let us know if you have any questions in the future, and I look forward to